Hi, this is the Tempter Podcast, Innovation at the Edge with Open Source. How can we build cutting-edge systems with the LLVM compiler? Today we're discussing Clang in the Yo distribution and Yocto in general with Khem, who's a maintainer of the Clang and LLVM technologies in Yocto. Hi, Khem. How are you doing?
Hey, Cliff. I'm doing well. Thank you.
Good. So maybe to get us started, Khem, if you could give us a brief history of GCC, Clang, and compiler technologies in general in Yocto.
Yeah. So Yocto is based on Open Embedded. Open Embedded is a cross-build infrastructure to build any firmwares, primarily for embedded Linux, but not limited to. But that's one of the big key use cases, and it has been built around Linux operating systems, and inherently it's obviously using GCC as the default C++ compiler, and C and C++ components form a large percentage of any embedded Linux system that you put together today. Kernel being written in C, and C libraries and so on and so forth. There are a lot of components, even though now new language runtimes are coming along. However, if you look at, there is still a fair amount of C++ and C in there. And GCC has been the default compiler for Linux systems forever. And that's where it started, even with Open Embedded. And along came LLVM Clang, which was Clang is kind of a C++ front end to LLVM. LLVM stands for low level virtual machine, which is essentially a retargetable compiler infrastructure. And when Clang came along, it was very fast, and obviously because it didn't have a lot of maturity at that point of time, perhaps didn't have all the kind of checks. But then again, because it was written from scratch again, it was very good at diagnostics for C++ programs. So it was of interest back then that, hey, can we get Clang also to compile Open Embedded based systems? And so we started this as a separate layer, the layer concept in project. So there is a meta Clang, which is essentially providing all the Clang related packages and logic to build a cross compiler using the Clang compiler.
Mm-hmm. So you mentioned LLVM is kind of a backend for Clang.
Mm-hmm.
So LLVM is also used with Rust and a number of other languages as a compiler backend. So the Yocto project, I assume, because we support that, we can more easily support Rust and a lot of other languages.
Yeah, that's a good point. So essentially, I think we'll talk about it more, but you're right that there are several other language runtimes which now use LLVM to provide their backend and machine code generators. And Rust compiler is one of the many, but Zig did that for a while.
Mm-hmm.
And there are a lot of proprietary compilers which I know have switched to using LLVM technology. They might be still using their own front ends, or they might be having some of their own optimizations and retargeted to their own architectures, but they have switched away from their own proprietary implementations to use LLVM for providing the compiler technology.
Sure. So I did a little looking, and it looks like GCC started around 2007. Open Embedded project began in 2003, and then Clang came around 2007. So that gives you a little bit of a timeline of the history of these projects.
Yeah.
So.
Yeah, that's correct. And I think the back in their time, like the diagnostics, C++ diagnostics were really not human readable, and we basically were always looking for any betterment for C++ code. C was okay, but C++,
Hmm.
you need to be like a C++ expert
Yeah.
in understanding that, and in
when
addition, you
when
needed to
compile
know the
yeah,
compiler.
when compiling macros in C++ goes bad, it's a mess.
Mhm.
And if the compiler can help you in any way possible, that's huge, because
Yeah.
we've a lot of us who have written C++ have been there.
Hmm. Yeah.
So meta Clang was a layer that you maintained for years, and now it's part of OE Core. What was the motivation for moving meta Clang to OE Core?
Yeah. So I think over a period of time, it started how it started, as an alternative compiler. And, my experiments were more or less on compiler interests, like, comparing optimizations and things of that nature. And you could do that on any desktop that, Yocto OE builds cross for, interesting architectures. So, it's going to give it an additional angle, right? And you'll have ARM, MIPS, RISC-V these days, and others that you can easily use as backends and provide that additional value. So, but I think what has happened is over a period of time, a lot of power applications have started using Clang, and a prominent among them is Chromium browser, and there's, I guess, fair bit of community which builds probably kiosk applications, or they use um, browsers as their runtime, or use browser for in various forms in embedded Linux systems. It's not used as a browser on your desktops how you use Chrome today, right? So
Hmm.
you build web UIs on top and things like that, and so they basically slowly shifted using Clang as their primary compiler.
Yeah. So we have the Meta Yo kiosk browser, or the Yo
Hmm.
Meta kiosk browser, which is a nice little kiosk browser, has a built-in keyboard and kind of all the features you typically need in a kiosk browser. And we're currently using the cute bundled version of Chromium. So we would build that with Clang then as well.
Yes.
Yeah.
Yes, and although the Qt version, they still maintain, or at least the Qt company, they keep it building with GCC. I don't know how long, but
Hmm.
essentially, that's an additional work now to do that. But the Chromium browser recipes in Meta browser has completely shifted to use MetaClang as a hard dependency.
Yeah.
And the way MetaClang was set up, that you could select MetaClang as, or Clang as, a compiler for a given package. So you could pick and choose per recipe or per package which compiler you want to use to compile. And, of course, your defaults being whatever your defaults are. Um, and that's the way it was being used. And in Yo, we basically went a little further, where we said our system compiler would be Clang, instead of GCC. And so, which means is that we'll compile with Clang, and then we'll make exceptions for packages that don't compile with GCC.
So most of the Yocto world's doing just the opposite. The default is GCC, and they make exceptions for Clang, but we
Hmm.
take a more progressive approach
Yeah.
and default to Clang, just to
Hmm.
kind of get the best technology, or at least for this, for
Yes.
our builds. Yeah.
Yeah, and I think that was the reason, and it was fourth, that we wanted to, because our main builds for Yocto's browser images were based around, the browser, and we wanted to compile the browser with the best technology it uses. and then extend that further to the whole system, because the compiler gives you a lot more optimizations if you use it across the system, because at times there are mix and matches do work well across component boundaries, but it's a homogeneous experience if you can provide a predominant tool chain to work with, and we were using Clang for that.
Mm-hmm. Yeah. So I think you mentioned at one point there were some other components. I'm trying to remember. Was it Mesa or something else that was pretty key to a lot of software that requires Clang now?
Yeah. So I think that's a good point. I think we kind of digressed and didn't cover the question. And so, I think the Mesa, but before Mesa, we were basically having live RSVG actually, which basically started using Rust, and then that's a key component for our graphics stack, or the default graphics test images in reference distributions that are built on by Yocto. And so that kind of like created a hard dependency on Rust compiler. So the compiler was migrated away from Meta Rust into the core, and that brought a version of LLVM, and there was like LLVM pipe backend support in Mesa for long, and it was using its own version of LLVM. So we had LLVM for target as a recipe, like a library. And the newer version of Mesa demanded Clang as well, because it has the Spur backend and others. They created dependencies starting with the latest major release 25 of Mesa. So for a release or so, we pushed it out because we wanted to do it, in a way that can scale well, not only for MetaClang's use cases, but also for any future use cases. Predominantly, how do we accommodate two different tool chains in the core that can set a precedent for, like, if somebody wants to add third tool chain, or want to add more tool chains and things of that nature. So we wanted to take some time to think about that, and then I think Mesa was kind of stuck on the previous version for a release or so, and then it was kind of the last thing that pushed us to bring it into the core. And so we started working at the beginning of this release, which was like 6 months or so ago, when we proposed the patches, and then we kind of reworked them. We got one version of the compiler in, and then we reworked it. Then we now separated it out into individual recipes. It was kind of a monolith. You build everything together, which is good in a way, bad in some other ways. That if you're not a Clang user, you find that, why would I build the LLDB or LLD? Can I disable them and things like that? So one thing we did was we separated LLVM. I mean, it's not yet applied, but when we apply it, LLVM becomes a compiler library, in common library, that can be used by all the compilers in core, including Clang, including Rust, and that will be really cool. So we did some work on that, on investigating on a Rust side, because usually what happens is, if you ship your own version, they will patch it. But we are lucky that Rust doesn't really apply much patches, on top of the upstream LLVM release, whatever it is. So once we get this separation of Clang and LLVM in there, we'll basically, the patch is already there, where we will be using a common version across both compilers. So we'll save time by, because LLVM is the biggest component in there to compile, as Clang itself doesn't take that long. Rust compiler itself doesn't take that long.
Yeah. That's interesting because every time I see Clang show up in my Yocto builds, I just know it's going to be a good long while till it moves on to the next step. So
Yeah,
yeah,
it
so
takes a while.
that's neat that you're making those components common, so we don't have to build LLVM twice.
Thrice, actually. So if
Okay.
you look at Mesa
Mm.
built their own LLVM in the past.
Oh, I see.
So we are already at a point where now Mesa doesn't do that. So we have
Mhm.
made 2 into 1, and soon we will make 3 into 1.
Great. Yeah, that sounds like progress.
Hmm.
Yeah, it's just fascinating that the Yocto build builds two different C++ compilers just to build what we need, and it kind of gives us a hint into the complexity of a modern Linux system.
Hmm.
But Yocto's designed to handle that complexity, and that's why we use the tool.
Yeah, yeah, and I think the historically Yocto's tool chains were meant to be pluggable, right? So because back in those days there were proprietary cross compiler tool chains from
Hmm.
different vendors, and people want to use those because they had support contracts with them, and but then they wanted the system build to happen through Yocto or Open Embedded, and so they needed a clean way of like inserting their tool chains, and so that's where like the external tool chain concept was
Hmm.
there in Yocto forever, and I think that has helped to keep the design cleaner, or at least has provided an important um, variable there to kind of like keep it objective. So um,
Sure.
with introduction of Clang, hopefully it's gotten into a little bit better situation.
Yeah. Yeah, this sounds really good. There's a lot of benefits to modularity, but there's also benefits to keeping these technologies in one repo
Hmm.
so they can be maintained more easily together.
Yep.
So yeah, that's interesting. So what are some other interesting things about Clang that other tools or benefits or things as you've used it, you've seen, wow, this is kind of neat?
Yeah. So there are the Berkeley packet filter BPF project, and that uses Clang LLVM. And this is BPF is interesting technology, right? It's quite
Hmm.
powerful. It's now supported in kernel. The VM is there, so you can write like BPF programs. Do a lot of filtering and stuff like that. Pretty neat stuff um, that you can do. I think on the network side, and so that kind of uses it. And I was talking to someone who mentioned it to me that how he discovered MetaClang was because he was trying to get BPF going, and then
Hmm.
BPF trace to be precise, and that's when he discovered MetaClang in Yocto subsystem. So one thing we did was MetaClang. We also kept some additional packages that were depending on Clang, right, which were external to Clang but were dependent on Clang, because that sounded like the right place for them until they are kind of part of some other layer. One of the things back then was that if they move to another layer, they will have a hard dependency on Clang, like browser did.
Hmm.
But browser layer existed before Clang layer, right? So essentially, we can do that. But for any other new components, we try to keep them close to Clang.
Sure.
Um, so yeah, I think there are several other components in there. Even within Clang, it's a rich set of components that you can benefit from. So it has come along and have started providing additional tools like linkers and runtimes, um, along with the basic compiler. And the LLD linker that comes with it is pretty fast. And there are benchmarks out there. I'm not going to quote them, but it's for large C++ projects like browser, Chromium browser or WebKit. It's like visible differences in building. So
Hmm.
if that really helps a lot. And I think it'll be interesting to see, the time we spend to compile Clang. Do we recover that otherwise, right?
Sure.
So, um, but um, but the linker is there, and they have a debugger. It's called LLDB, which is essentially pretty neat. They also have a LLDB server, which runs on the target, and then you can run the LLDB on the host,
Hmm.
and it has a pretty nice Pythonic interface, to program your debugging, um, which is like the Python CLI is very powerful, and it also provides you C++ library nowadays. It's called libc++,
Hmm.
and also it provides like built-ins, which is kind of the compiler built-in implementations, um, and so these are like core tools that you'll expect in your tool chain, but in addition to it has additional tools like uh, Clang Tidy, which is a linter, for C++.
Hmm.
And it's a configurable linter, and it gives you a nice YAML sort of configuration. So everybody has their own programming styles, and every project has it. So you can define what you want to do, and you can configure the linter, and so Clang Tidy is pretty interesting and pretty neat tool. And then there's a for styling, there's a Clang format. It checks you for that.
Hmm.
For static analysis, there's a scan, Clang scan. Um, so we do have the support for it in MetaClang. So it basically is a static analyzer, and it gives you really a report that you can open in a browser and then surf through the code, and it has a lot of annotations in there, gives you a lot of hints.
Hmm.
So yeah, so those are additional tools, and there are like Bolt, which is a post linker optimizer, and of course, like the LTO and other things which are in other compilers as well. But all these tools are pretty interesting, and they make a quite good collection to go with as a developer.
Yeah, I use Clang format a lot.
Mm-hmm.
And there's also a language server. I'm not sure if that's part of the Clang
It is.
project, but I use that a lot. It works good.
Yep, Clang D. Yeah,
Yeah,
yeah.
Clang D. Yeah.
Mm-hmm.
So yeah, even if you're not doing embedded development, there's a lot of technology out there that's very interesting for developers.
Mm-hmm.
One thing that's been interesting in the past is the Linux kernel has traditionally used GCC extensions. The way
Yeah.
it defines structs and different things like that. So does the Linux kernel compile with Clang now?
Yeah, it's a very interesting. You know, there was a project in the Clang built Linux,
Mhm.
and it ran for a while. There was a lot of contributions that were done under that project. Which was basically trying to get the Linux kernel compiled with Clang, and there were a lot of discussions, on various changes. Clang didn't implement all GCC extensions, and obviously, kernel did use some of them, but then Clang did implement some of them, over a period of time, and some of them were like, not implemented in standards, which Clang didn't implement. Things like variable length arrays in structures, and some subsystems in kernel use them, like networking subsystem and all.
Mhm.
But I think with some deliberations all over, today we can compile Clang kernel with Clang, at least for x86, ARM64. I think even for RISC-V, I have compiled it myself a long time ago. I haven't done it lately myself, so I don't know where it stands. But it's pretty. Um, I would say that I think it is in a good shape when it comes to the kernel piece. Um, Although it is not default in there, so if you just check out and build kernel, we'll just use your default GCC.
Sure. Yeah. So, is there anything else you'd like to share about how we use Clang and Yo or any other interesting aspects?
Yeah, I think there are basically LTO. It provides something called thin LTO. Both compilers do LTO, but thin LTO is interesting, which is basically halfway because LTO needs a lot of time and space. Thin LTO can get you like best of both. I would say like a uh, not best of both, but more like a compromise. Um,
So, what is LTO?
oh, sorry, LTO means link time optimizations.
Oh, sure.
So
Okay.
yeah, so what it does is it basically compiler generates an object that is not final object. It has intermediate representation, and then it compiles all the uh, you know files, and then feeds that back into the linker. And linker has the view, because all the files are now available, and it calls back the compiler again because now it has a view of not only single file but the whole binary that you're trying to compile. So it can see what further optimizations it can do. It can
Mm,
find more opportunity to delete like functions or dead code. And so it's so basically that's what LTO does, is it basically generates that mechanism in place. So it has a linker has a plugin to reinvoke the compiler, and so it's all happening behind the scene.
I see. Yeah, well, this all sounds very interesting. And if you want to use a embedded Linux distribution that leverages the latest Clang technologies, check out the Yo distribution.
Mm-hmm.
It's where we try to push things forward. We do monthly releases,
Mm-hmm.
and it's worked out pretty well.
Yeah. So if you use like any of the AI frameworks like PyTorch, TensorFlow, you'll find Clang everywhere. At least it's not the AI framework itself, but any framework that you're building, they are most probably being built using Clang.
Hmm. Yeah, as things become more complex, it'll become even more important
Mm-hmm.
to use the latest technology, or at least have it available. And
Yeah.
that's what we strive to provide with the Yo distribution. So,
Yeah, and I think one of the things for long term that we wanted to see is heterogeneous compiles, because what we
hmm
are seeing will go away towards where we are compiling a program that would run not only a general purpose CPU that we have done so far, but it will be more distributed, where you'll have accelerators like GPUs or maybe another specific processing units. And I think there are like languages like modular which are coming along, which are trying to define these heterogeneous memory views for programs. And obviously, like this is kind of at the center of it. And for immediately what we are looking at, for example, um, GPU compilers, right? They
hmm
have like ROCm. They use something called HipCC, which is Clang based, and there's a CUDA backend as well, which is based on LLVM. All the AI compilers, for example, there's a technology in Clang called MLIR, which is like multi-level intermediate representation. It's very unique and powerful because that's what people are going to develop all these dialects, right? Any kind of AI dialects that you want to do, and you just need to write a front end which can talk to him, or generate MLIR, and then there onwards the compiler will take it. So I think MLIR will be pretty powerful for implementing these kind of code generators.
Sure. Yeah, it will be interesting to see how this all comes together. But one thing's for sure, it's not getting simpler. I mean, the stacks are getting more and more complex. To keep things working, often the only path is forward. So,
Yes,
yeah.
absolutely. And I think all these tools do help in making these stacks work well, because obviously when it gets complex, you need rich set of tools. We didn't talk about sanitizers, but there are like so many sanitizers and fuzzers that come along with Clang as well. So you can
Sure.
basically have a good set of tools in your kitty when you go attack these powerful and complex systems, and this will certainly help you.
Yes. Well, thanks for listening to this episode about Clang in Yocto. If you have any questions or comments, please reach out to us at the Tempter community or contact us directly. Thanks for listening. Till next time.
Thank you.